Anyway, all right. So today we're going to be talking. I'm going to be talking. You're going to be listening, and when you're going to be listening, you need to ask questions. And I have some swag, which is awesome T-shirts. I don't have these T-shirts because they have an awesome Kafka logo on the back, and I don't have this kind of thing. How many of you guys heard about Kafka in general? All right, cool. So we're in the right place, we're doing the right thing. It's impossible to talk about something versus without putting this picture on the slide, right? The Batman versus Superman. So we're going to be talking about stream, which is like a fast and like fast-moving data processing things, versus batch, which is slow and bulky and stuff. And we'll see how it goes. Just a couple words myself. I work as a solutions architect with Confluent. So what I do at my day-to-day job, I work with customers. I work to help solve their problems, and this is how I get my money. What I actually like to do is be developer advocates. Not only stay here and preach about our stuff, but come to conferences or like meetups like this and listen to people and get a feedback about our product and make it better. Also, like, I'm all around the internet, so please go follow me. I'm a very interesting person. All right, so also being on the conferences, I also building highly scalable Hello World application. So hopefully we'll see some of those today as well. All right, without further ado, so the batch processing. How many of you knows like where this term came from? I don't know, like nobody knows, but there's a couple of things that you can find on the internet. And one of the things that I found when I was researching about the batch processing is actually there was a batches of used tickets that the people collected in London Metro in 1939. So basically, they did the batch processing, literally taking batches of used tickets, and try to figure out how many people went through the to the subway, through the metro, over the day. So here now you have it, right? Okay. So from perspective in general, perspective of data processing, from perspective of data processing, from perspective of any type of interaction with data, I think has two parameters, right? The first parameter is time-based. Like some events that we capturing in our systems, it might be event related to some financial transaction, some event related to some of the user interactions. So it's always time-based, right? And if you kind of take this idea from the real world, you can think that you're always moving forward, right? You're always moving forward. You're collecting events that happened in the past, right? And because we're moving forward, this data is inherently immutable, right? So you cannot change the events that happened in the past. So this is why I think some of the technology decisions for past 30, 40, 50 years is actually, affected the way how we represent the data and how we perceive the data, right? So when we're talking about, for example, we're storing data in database, we can do create, update, delete on the same record, right? Because this is the way how the SQL tell you to model your data. But inherently, you're trying to capture that events that already happened in the past, and you cannot actually cannot change them anymore because they happened in the past. So that's why I think we need to treat them as inherently immutable. And when I'm talking about create, update, delete, so if you think about the data as a sequence of events where each event is immutable, you cannot change this particular event, but you can send different event that will change our perception of this data or our view to this data. So in this case, there's no update, right? There's a create, read, and you have update in the form of another create, but it's going to be another event that happens with data. And there's no update. So when we're dealing with the processing of the data, essentially we're applying some sort of function to the stream or to the the batch of events that we have. So applying some sort of function. This can be a projection that will create some sort of subset of your data. It can be aggregation that will combine two data sets together and represents the second one in different form, or it can be join, which is aggregation is actually creates like smaller version that will give you a result, some sort of calculation like a sum or average or something like that, and join that will provide you data set that will compose from data sets and will create the third view of this data set. As a representation, this like SQL is something that we already know for quite some time, and SQL is basically your processing function, right? You're applying this function to data set of data. Here's your projection, here's your aggregation. There's no joint in this case. All right. So, but inherently, technology with SQL limit or like a SQL approach or relation approach limited us in terms of how to scale this data, because what we learn over like I learned it over like 10 years because I'm still young. And I can say like I learned the SQL in university when other people already making money on SQL. But I still think this SQL affected the way how we affected the brains and the way how we think about the data. And some of the things that affected the most is the third normal form, right? So we know the third normal form is the canonical representation of a data structure because there would be no duplicates, there would be no some extra information, and you composing your data model from object world where we have inheritance, when you have an extension and things like that, into the deconstructing into using joins, you forming your actual view of business. So you have multiple tables, you do joins, and now you have this materialized view of the things. However, recent events, like 5-7 years, and rise of NoSQL databases that don't have relational model underneath show that SQL model doesn't scale well in what they call web scale, right, fashion. So when they have a enormous amount of data, data is highly, the huge volumes of the data, and it's not possible to fit this in a relational model. It's not possible to fit it in one computer. So that's why the normalization is something that we're trying not to do with NoSQL databases or data stores or any type of data storage systems. So data getting some extra information. So now it's okay to have denormalized version of accounts, which will contain some extra fields from some additional account information, including like address, for example. If it's some sort of customer or client, we can embed this. And so couple years, we see rising of this NoSQL and highly scalable systems. And how to process this at like a web scale data, the data that already not stored in one computer, stored on multiple computers. There's a lot of data. We know how to store it efficiently. So I'm not going to talk about things like consistent hashing, partition, sharding, but these things actually led us to collecting a lot of information. Like over the years, the organizations, they collecting information in many systems, and one of the when we're talking about distributed systems, it's also virtually impossible not to mention the CAP theorem. How many of you heard about this? CAP theorem, consistency, availability, partition tolerance. This is 3 characteristic distributed systems. You can have only 2, which is, it's vaguely explains many systems, but it's not the right thing to use to explain all systems, because there are trade-offs. Many systems has different ways how to approach the problem, different ways how they think about certain like consistency, for example, availability, and how they treat partition tolerance, that type of things. However, at the time, like 5 years ago, there's a gentleman, he was working on Twitter, and Twitter, as we know, is a web scale company, right? So they have a gazillion tweet database, so people just tweeting. How many of you guys have Twitter? Yeah, it's my Twitter is over there. You can follow me in Twitter and send me some tweets. So this guy is actually start thinking how to process this more efficiently. And in the concept of this kappa theorem, he was thinking about how to overcome this limitation that the system cannot have all these three components. Specifically, how to deal with the partition tolerance and how to deal with it in the systems. And one of the things that he kind of come up, it's not like it directly targets this kappa theorem. I guess it's more like a marketing approach to sell his vision about processing data. But he actually came up with this idea that after that they called lambda architecture. So the basic lambda architecture is the way how you organize data processing pipeline in a batch fashion, right? So usually, yeah, it's kind of funny, like ACID, which is we have in databases, and in modern distributed system, we have a base, which is basic availability and simplicity. And oh, I'm sorry, you don't see it. All right, so that was like funny joke. Anyway, so the lambda architecture in this case has couple layers, right? So there is some sort of system that injects or like ingests events into our system, and there's a speed layer and there's a slow layer. So some of the data can be processed in using this kind of like system, which is like Storm, one of the system that the guy is invented. And data can be processed into two layers. Once you have requirement to get more or less approximate ballpark of, I don't know, user clicks, you're using this speed layer, because speed layer is actually allows you to get more or less fresh data faster. However, if you need to have more accurate data, you run this like, for example, Hadoop job overnight over all sets of data that you collected for the day. So the difference here is that the speed layer actually needs to have less data, and it might not take into account some of the late events. We're going to talk about the late events a little bit after. So some of the events that you want to get overall picture from your system in 1 p.m. But maybe some, because of the speed of light, speed of the systems that ingesting this data, some of the events will not arrive at 1 p.m. So that's why you will get the ballpark, and overnight when they run Hadoop job, when you know that all events were stored in your HDFS, you can run the job, and after that you get better approximation or better results. And usually application dealing with this like serving database, which is essentially, sometimes it's a key value store, because you don't need to query it. You just need to get like a fast representation of this materialized view. So yeah, Hadoop MapReduce. And actually, I like this picture from perspective of, how many of you watching It's Always Sunny in Philadelphia? That's unexpected. Anyway, so basically the lambda architecture and the approach for batch processing data pipelines actually created a lot of different beasts in open source world, and it's very difficult to in very short conversation, like explain all the things, and the people over a couple of years, they come up with different ideas, different ways how to solve these problems, like basically how to process big data, right? So there's Hadoop, that essentially implementation of Google idea of MapReduce. There are some of the things like Spark, which takes there was a Storm before, it was created in Twitter to also process this processes this data storm was used in not in batching like or MapReduce style, but more like streaming style. So it was one of the first system of stream processing. After that, there was a Spark, which was also kind of inherited some of the batch processing capabilities, plus introduced to some of the stream-like approaches like Spark streaming, etc., etc. So there's Zookeeper that helps to build the clusters. There's a Kafka that helps to move the data around. So many things, And the Lambda architecture is actually becoming like a very complex system to deal with, to maintain, and in general, not very simple to use. So the basically results of computation, they will be placed into this like a serving layer, and the serving layer will be displaying this information in the forms of view, right? So we have some of the events. On the timestamp, we run the MapReduce. We have hourly results, and at the end we'll run. At the end of the day, we run another job that we have count per. See this elephant DB. So there's some sort of another database that was initially proposed because I took this picture from his blog. So basically, Lambda architecture. Key takeaway from here: 2 layers. One layer, it's a speed layer. Another layer is a batch layer. On speed layer, you're producing the results that very close, but not very accurate. And the batch layer, it's usually slower, but get more accurate result because it has all data in a place. Now, over the time, the batch layer becomes more and more tedious, and people want to get like they say, okay, why we cannot have the accurate results, but with real-time type of fashion. But stream processing is not only about real time, right? So I just want to make it clear that you also can do batch type of processing using stream processing tools. So you can think about this as a batch, as just the option of. You can think about batch in the context of the stream processing as just one of the options where you have a finite stream of data. And also we're going to talk about this a little bit later.
There's a difference between bulk processing and batch processing.
I said bulk?
Yeah, bulk.
Yeah.
You're saying here's 50 independent, events, versus if you're saying like batch processing, right?
Yeah.
You're looking at it that way, or are you looking at it as real batch processing?
No, batch processing, what I'm implying by batch processing is when you have all your data in place when you start processing. So when you're doing the processing, maybe I used the wrong word, sorry about that. So when you start processing, you know that you already have complete picture of your data, so you just run this. Yeah, exactly. Yeah, exactly. Yeah.
Eventual consistency.
Exactly. So it's not eventual consistency, it's already consistent. So comparing to the speed level, where you have an eventual consistency of the data, and you have some sort of like close but not accurate result. Sometimes in certain cases it's well enough if you need to have a ballpark. How many thousands of clicks we have? Like 5,000 or 6,000. You don't care about the actual if you miss some of the clicks, right? So it's going to be like 5,005. But in some cases, like when it's information from the sensor that collects the temperature, collects the gas concentration, collects the gas pressure information, things like that. You don't want to lose this one, and you want to have accurate results. So this is basically a difference between, you collect the data and calculate something. With stream, you need to use this data to get more accurate picture of your system, to get more accurate feedback to the systems. So like you see that, okay, the pressure is too high. We need to start another workflow that will shut down this, or start additional pumps to help us mitigate this high pressure. So let's talk about stream processing. So basically, in stream processing, in stream processing world, and so there's another thing. I don't have slides this, but there's another thing called kappa architecture, which basically defines how you would process like stream data. And the kappa architecture is evolution of lambda architecture. It simplifies the things. And there's one thing that sits in the center here is a oops. Whoa. What was that? Supposed to be, yep. Yeah, streaming platform. So the streaming platform in the center is essentially idea that appeared from also the web scale company, also data-centric company at LinkedIn. At LinkedIn, they have this problem where they have multiple interconnected systems, and there was very difficult to get one system to get data from another system. This is something that we call right now microservices. They have it like way back, and to solve this problem of tangled or interconnected system, they had to come up with some idea that essentially became a what we know right now as a Kafka. So they built this system that was based on the concept of the log, and we already know this concept from database transactional log, right? So the database essentially presents tables, presents views, and other artifacts based on stuff that happens on top of transactional log. If you kill your database instance and some of the tables were corrupted, database can run the process that processes this log and reinstate these tables, reinstate these views. So this concept is not new. So it was used in database a lot of time ago. So these guys were sneaky, right? So they told you that, okay, you need to learn SQL, but they underneath they used much simpler and more straightforward approach. So the log, it's append-only file. So basically every event will be written in the file, this concept is actually pretty powerful. So they build a system that actually has not one log, but multiple logs. The logs are distributed, so they can store the data not only that fits in one computer, but data can store on multiple computers. Also, they provide the way how the different system can communicate this in a pops-up fashion, but not in a way that system will be overwhelmed with incoming events. Right? So if you're interested of the data, you can say, okay, so I need just this subset of the data and pull this. If new data will arrive, it will be stored in the streaming system in the Kafka, and next time when you can collect this data on your own pace, and data will not go anyway. Comparing to GMS system, when data was consumed from the queue, it will disappear. So in case of failure, you can always read this. So things that right now known as event source, they were used these ideas were used in Kafka. Now, and after a certain time, the founders of this project, they saw the value of this, and so what we're doing right now in Confluent, we're building a streaming platform, and we want to make sure that every company has streaming platform that serves their need, because we believe it's a future of dealing with data. And many applications can, including some of the application from like a big data world, like Hadoop here, and some of the K-value storage, even database. So database is actually a very interesting piece, because remember when I just talked to you about this like transactional logs that you have in database, and how database engine reinstantiate tables from it, we can also do this vice versa. Like, how many of you heard about this Martin Kleppmann, the gentleman who was one of the guys in LinkedIn at that time? He also was working on Kafka, and he has like very famous presentation, like turning database upside down, when he was talking about, okay, so database already doing this internally. So if we will read stream of events, like mutation events, of the data. Like when we, instead of reading all this like inserts, update, deletes, we can listen on transactional log and collect this information. In the future, we can always reply this event and create the same view of our data, the same way as a database doing. So in this case, there are change data capture utilities that allow to listen transaction log of database, avoiding dealing with like high-level abstracts like SQL and relational schema. Now, okay, let's go first. So next, how to process data. So one of the things here is stream processing. So stream processing, this is something that we're going to be focusing on this particular set of slides. Now we do have system that collects our data. So we can imagine that we can consume the data in the same way as data is arrived. So in this case, we have an infinite stream of data. But how to process data? And many systems, including like Spark, including Flink, including there's a system called Hazelcast Jet. They follow this the pattern of building a computational pipeline, and it's called DAG, direct acyclic graph. But there's something that it's internally, but this model actually explains very well how data can be processed. In the vertices of this graph, you can have actual process node. And here's the difference. Here's the difference how the different systems deal with this processing, right? So when we're talking about the stream, like a pure stream systems, they usually dealing with the processing like event at a time, right? So the processor API-wise is dealing on one event at a time, and how the event will arrive, it's not the part of the DAG. But there are systems like a Spark streaming, which is not, even though it's called Spark streaming, but actually it's a micro batching, meaning that the processing engine focused on replaying whole DAG, but for only small subset of the data. So this is why it's a difference between micro batch or like batch system and stream system. It's just how they process events. So one event at a time, it's a stream system, and the micro batch, like replaying whole pipeline of things on smaller subset, it's a micro batching. Now, and these edges of this graph, they actually represent a data flow. How one processor sends the data to another processor in the pipeline, right? And I will show this DAG in a code in a moment. Oh, okay. Couple words about word count. How many of you seen the word count demo in big data world? Any type of, like people like, yeah, whatever. So it's actually interesting because word count is not distributed task. It's not distributed task to solve. You can use the WC command and count words, right? So why is that? Reason for word count, why it's considered to be a Hello World application in distributed, or not in distributed, in general, in the big data and things like that, because it's simple, it can illustrate the concepts, and the data essentially here can be represented as a stream of words, or you have a file which is batch, so you already have this data. So, and it's relatively, another point is here that there is no algorithmic complexity that can, you cannot imagine different algorithm that will speed up computation by, in multiple times, because there's an essential part. You see the word, you're saying, I saw this word. You put in 1. You see another word, you put in 1. You see another word, you put in 1. That's it. So there's no way how you can optimize it to make it faster. So that's why sometimes the word count used as the benchmark, because it shows the overhead of actual engine, not the algorithm. So that's why simple algorithm can break a complex system. So because we're a little bit right now of time, I will focus on one particular framework right now, but essentially the concepts that many modern the stream processing frameworks, namely most popular, it's like Apache Flink, the Kafka Streams, obviously. We can say the Spark streaming, Samza, one of the first frameworks that introduced this like concept of stream processing. They have a similar concepts, but the details in different ways implementation I'm going to be talking about a little bit later. So okay, so apparently I do have IntelliJ. All right. To run this example, first of all, I need to have this like streaming platform somewhere. So obviously, for me, and now I think it's obvious for you, I use the Confluent platform, which is all right, so let me explain one thing. So there is open source Apache Kafka. People asking like, Confluent, what are you guys doing? So there's open source Apache Kafka. You go into the kafka.apache.org and download the Kafka. Boom, you're good. Now, so what is the Confluent platform? People asking. So the Confluent platform is actually it's a complementary thing to Apache Kafka that provides some additional nice things. So for example, if you're writing applications like streaming applications or any like data pipeline applications, and you need to deal with the languages that don't have native clients, you can use things that called REST proxy that allows you to get a message out of the Kafka using REST interface. Or you're running JavaScript application, web application, you just need to, fetch the data from it. There is a REST proxy that included in the Kafka platform, in the Confluent platform. Now, in a more complex world, when you have multiple applications that need to interchange the data, usually we need to deal with situation of schema management. So we're not just putting some of the random stream of bytes. Kafka actually, Kafka don't care about if you're just putting bytes there, because Kafka don't do anything. So Kafka is just moving data, and it does it very well. However, we are writing applications that has some of the business logic, and we actually care about these bytes needs to be represented in some sort of object. So we need, in this case, we need to maintain the way how we can deserialize this stream of byte into our object. So in this case, schema, which in simple cases is Java class, it's also our schema. It comes into play, but in a more complex scenario, when you need to interchange between not different systems, but also between different languages or systems written in different languages, you need to have some sort of schema that can be portable across multiple, because Java classes, they're not portable. You cannot deserialize a Java class in C++. So that's why there are things like protobuf, Apache Thrift, there's Apache Avro, which is very popular from the Hadoop world. So the Confluent platform also comes with a schema registry that allows you to manage different versions of the schemas. So you have one system that push data in version 1 of the schema. Another system needs to understand this data. When the system 1 will change the version, another system should not break. Right, because it needs to understand like previous version of the schema, and if needed, it needs to get updated. So, and plus there's a framework called Kafka Connect that allows you to kind of like integrate without coding different systems. The Confluent platform comes with some of the predefined connectors. In my case, I have this like Confluent platform here, and there's a very nice tool that I'm going to be using that it's called Confluent CLI. So what it does, it actually allows me to do some of the operations with data. It allows me to start, stop, and do various things with components of this platform. If I'll do this Confluent CLI list, so it provides the way how, what kind of components I do have here. So first of all, Kafka uses Zookeeper for basically literal action and storing some of the metadata. These days, Kafka we're trying to use like a less and less Zookeeper, but still we use Zookeeper. So that's why like we need to start Zookeeper first. And the cool thing about this, you can use it for development if you're doing anything with Kafka. So the cool thing about this particular tool is that it knows a dependency of each component. So for example, if I want to start, for example, I do Confluent start Kafka. It knows that Kafka depends on Zookeeper, so that's why it needs to start Zookeeper first. So, but I'm not going to be touching other components of the system right now. I just started Zookeeper and I started Kafka. And also another thing very cool for development, you need to know, okay, so you start the Kafka, but where's the logs, right? I can do, and after that, oops, log. Yeah, and after that I can get the output of, the output of the Kafka process and things like that. All right, so for now it's enough. Now, so I do have my streaming platform app up and running. Now I need to have two things. So first of all, I need to populate this with some data, right? Some data that I will be processing. So Kafka operates with the concept of the topic, so I need to create these topics. So I will be using this word count input. So in this case, I will be using this topic as an input. So I will just dump some of the things in it. Boom, and I will create topic output. So for the output, result of my processing will be placed in this topic. So it's kind of a little bit maybe unusual, but this is the way how the Kafka Streams, as a particular example here, is doing things, because it uses. The Kafka Streams is the ultimate user of Kafka, because it uses Kafka for getting data, for putting data back. It uses Kafka for storing the change log, for dealing with the fault tolerance. I'm going to talk about a little bit later. I have some slides about this one. So. And the good thing about this, you don't, as a developer, when you're writing this Kafka Streams application for data processing, for stream processing, you don't need to actually like worry about all the things. You need to know some things, but you don't need to worry how to create this, like some additional things. So I have two topics. Now I do want to have. I want to populate this with some of the data. So let me actually run this. So I will do this in another window, because I want to have another window open as well. Okay, start. So how I will populate this? You probably don't see anything, right? All right, so how I will populate this stuff with something. So there is the bunch of command line utilities. In this particular case, there is a Kafka console producer. So, and the cool thing about this, the console producer just expects me to enter something. Hello, hi, hello. Right, so I just entering some of the words, and after that I can stop this. And to demonstrate the result, I will start another utility that called Kafka console consumer. So what it does, so the consumer connects to this server, which is my Kafka server. It will read topic word count. This guy from beginning. It will use default formatter. It will be print key values, and also it knows that the string is going to be my key, because in word count scenario, the key will represent word, and the value will be number of how many times this word occurred. So I start this, and it will run in, for quite some time. Now, so let's take a look. So this is like a setup. So now my streaming platform already has some data, even though it's not that fancy. We have some like hello, hi, and fill a JUG, some data. Now, I do have my application. All right, so now it's kind of, I think, the deal breaker. So when you, how many of you guys use like systems like a Flink for writing application, for streaming applications, or similar things? Spark, okay. So what you need to do when you need dealing with Spark? First thing, you need to start some sort of cluster. So after that, you need to write your driver app. And at some point, you start thinking, okay, all right, so it looks like the concept of processing and the clusters setup is leaking to my business logic, because you don't know which part of the code will be running on your worker, how they call it, driver application, and which one is going to be running on, oh, I'm sorry, why am I running this one? So let me presentation mode. And the main idea in the Kafka Streams and things that we think that people need to focus is on building apps, not building clusters. So with the Kafka Stream application, it really doesn't matter how you're going to package this application. You always know that this code will be executed in the context of your application. Kafka here would be ultimate storage of the state, ultimate source of data, ultimate sink of data, or like result storage. And in this particular case, as you can see in my, how many of you guys are using Gradle? How many of you guys using Maven? I see many people doing poor life decisions. Use Gradle. Anyways, I'm just kidding. So it really doesn't matter. At some point, when you start, I guess my mom's called it like maturity. So I'm not participating in holy wars anymore. Like I'm not participating in the world like Java versus Scala and stuff like that, because I don't care. I can write any language, so I don't really care how to express some of the thoughts. And so it's, some of the tools are suitable for certain things. I think the Gradle, it works better for me in my personal project, but everything what we do in Confluent and with Kafka, it's using Maven. It is what it is. Anyway, so as you can see, there's one dependency that I have in my app. So and the two dependencies for logging, but I don't count them as a dependency. Now, so this is pretty much it that you need to include in your application to start writing a streaming application. And essentially, the logic of this application is here. So this is my word count, right? So this is what I'm sorry. This is my word count basically, and there's no like a cluster setup. Everything will be running here, but internally it will communicate with Kafka to read data, to write data. So let me talk a little bit about what we see here. So first of all, there's the concept of Stream Builder that allows you to configure this API. So there's two APIs. This API that you see right now on the screen, this API that you see on the screen right now, it's that we call it like DSL API, but I'm more in favor of like Fluent API, because it's more like that allows me to build this kind of nice Java 8 streams looking API. But there's also low-level API that this API will be translated, which is a process API that I was talking about earlier today. And the process API actually defines the way how you will deal with each individual message. So the way how it looks like, because we're reading this from the topic. So in this case, we're creating a stream from a topic, and here we're defining the way what kind of stuff we have in this topic. So essentially in the topic, because in our producer we didn't enter anything. We didn't enter anything about like a key. It will just, will be null as a key, but the value would be string. Now, so for each element of the stream, we start doing this kind of transformations. So the first one, we will turn, if we see this text or line of text, we're going to be splitting this into to get individual word. So this pattern is basically just a regex for word. So the map values, map it actually at the function. How many of you guys actually using Java 8 streams API? All right, cool. So in this case, I don't need to explain this stuff because it's exactly the same stuff that you do with Java 8. There's mapper function. You can map for the key. You can map for value. Only difference that when you start doing transformation of the keys, it will trigger repartitioning because it will affect the way how the key is distributed. So it will redistribute data in Kafka topics a little bit different. So in this case, I'm just interested on the values only. So that's why I'm just lowering and cleaning up. I'm throwing away some of these smaller words. And I'm just writing it back into the word count topic. So when I will start this, as you see here, it's a public static void main application. I just specifying where's my Kafka server, where my Kafka cluster is running, and pretty much it. So I'm just specifying serializer for default serializer for key values, just default stream deserializer. So when I run this application, I should see something starting getting in the console. So my consumer is going to be listening for this word count output. So as you can see, there's something that was spit out from the thing. And as you can see, I have hello 1 and hello 2. So the reason why you have this, we have this on the screen is that because the way how Kafka dealing with the things, it's storing them in the topic. And remember, in the very beginning when I said we're not modifying in place, the first state of my hello 1 pair was hello 1, right? So in the very beginning, when the first time see the hello word, I just placed this hello as my key, E1 is my value. But hello 2, it was another event. So I didn't modify my result hello 1. So essentially, in my output topic, I have a whole history of my data processing, like every step that happens. And I can continue doing this stuff here. Boom, 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 boom. But it's not fun, right? So most important book in my school program was War and Peace by Leo Tolstoy, and it's a huge book. It's very suitable for big data processing. So I will be using this one to count words there, right? Kafka console producer, and I still have it in my old place in my Hazelcast projects. So War and Peace. So I'm actually, what I'm doing this right now, I'm depiping this file into console producer. So I'm just dumping every line of this file into Kafka producer, and my stream processing application will start counting words as they arrive, each and every event. And this catch up because the console is inherently slow because spinning up. So there's lots of interesting things that we can find here. It found something like, for example, okay, let me show you something. Because I know, and you can potentially figure out, there's three main characters in this War and Peace, if you ever read this. It's a pretty good book. So there's Andrew Balkonsky, he's a knyaz and stuff. So his main character, and I can figure out like his name is appeared multiple times. So what I can do here And I will start my console producer, and I put Andrew here. And what I can see, it should pop up here. So this is how many times, like 1,141 times this name appeared in the War and Peace, right? So, but because I added Andrew here, so it pop up here. Somewhere here in this output, I can find this Andrew. Also, there is another character, but I don't remember how to spell him correctly. Pierre Bezukhov. Yeah, so he also pops up here. So this is, and the difference between the batching, the batch processing of the data and stream processing of the data is that my application runs constantly. It's still waiting for new data. And as I entering here, new data is arriving, and I can do different computation. So one of the things that I want to mention here is that nope. How about nope? So this particular case is a stateless except. So all this transformation is pretty much stateless except the count. So then this count is actually needs to collect the state of the result. So it needs to sum it. So for that, it uses some local state. Also, it pushes some additional state. Also, let me show you one thing here. So there's a command topics. Topics. Well, it should be list or something. Where's list? Yep. So there's an interesting number of topics that appear here. So first one, the word count, this is what we're using for input, and the word count output that we use for output. However, there's a couple more topics that was created here. So first one is the word count app. This is my application. I created this this name over here. So word count app. And so this guy has changelog, which contains like everything that happened during this transformation. So even though it's transparent for developers, but Kafka also tracking stuff internally. So the next time if my application fails somewhere, it can start from the place where it left off. Also repartition, this information about in case of we need to do something with keys, so we do some modification with keys. In this case, it's going to be triggered repartitioning. So this information also stored here. And before we go, I will show you a couple more slides that will explain a couple more things about stream processing. So a couple things about fault tolerance, right? You can say, okay, Viktor, so we're running this application, but it failed, right? So how we can do this? Data is too important to store it in one computer, and for that we have a cluster. So the Kafka will store this data. Kafka is bulletproof system for storing your data. Some people saying, oh, Kafka is not persistent. I was reading these comments. So the New York Times, they actually published the article about how they use the Kafka to. So basically, they moved all their the published materials starting from so basically 161 years of professional journalism is now stored in Kafka, and some people in Hacker News in comments are saying, "Oh, it's Kafka is not durable; it will not store the data." So it will store some data, and it's bulletproof. It's already proven by companies like Netflix, LinkedIn, and Microsoft. So they pushing trillion messages through the Kafka every day. It's called like a trillion messages club. So right now it's Netflix, Microsoft, and LinkedIn. So the basically idea that you're running your application and your application has a store. So first of all, Kafka Streams has a local store. So there's some of the state of the application also stored on the local store, which uses RocksDB, which is I guess it's a Facebook open source. This project is a C++ database, also key value, store lots of in memory, and it uses used in Kafka Streams. Now, but the state can be, you want to extend. For example, load too big, or you want to have it for a situation when you need to have like fault tolerance and things like that, so you can expand it. You can start another instance of this application, and the Kafka stream will figure out and how to rebalance the work and how to consume data from different partitions in the way that is going to be parallel computation. Or you can also shrink back. So for example, you did this computation for Black Friday, and now demand goes down, so you need to pay for expensive hardware. You can shrink it down. And the Kafka streams also support this use case as well. Plus, there's a changelog. You've seen this special topic changelog that contains some information that happens in your application. So if one application failed, another application can take over by reading this changelog. So now there's a couple of things about infinite data, how to process infinite data. So there's everywhere in our life there should be like trade-offs. In stream processing also there is a trade-off. So there's no like infinite, right? Because there are multiple things that might happen in the system, some late events, things like that. So we need to somehow adjust the model, processing model, to fit it into this to handle situation of the real world that will be modeled in our system. So in this particular case, we're talking about there should be specific time semantic. In this particular case, Kafka Streams, alongside with other stream processing systems like Beam, Flink, they support two types of event. So event time semantic. Event time semantic means that when this actual event occurred. So not when the event appeared in the system, but when they actually occurred in real life. And plus, like processing time is actually event that when we start doing something with this data. How many of you guys seen Star Wars? All right, so Star Wars? So there's like some popular movie about Star Wars. So actually there are 7 movies these days. And to explain, I guess this is very canonical example how you can remember what's the difference between event time and processing time. So basically, you know that a story starts in The Phantom Menace when the Anakin Skywalker was racing in the home-built racing car and things like that. And The Force Awakens, it's something that happens further and when the Anakin Skywalker already died. And there's only helmet of him. But there's a processing time. So there's something that how these episodes actually appeared, right? So in general, the history flow in Star Wars Galaxy is as we have here, right? In this event time, right? This stuff. But the processing time is different because the first episode, A New Hope, aired in 1977. So if you want to explain someone what's the difference between event time and processing time, use this picture. It's a pretty cool picture I borrowed from my colleague, Michael Knoll. He's a product manager with Kafka Streams. It actually explains how things can be applicable in real life. Now, so how we know how to deal with the different types of events. There's like event time and the processing time. Now, how we will deal with this data? Data is still infinite, and how this like processing time and event time will help us. So there is a concept of windowing that basically allows us to group events and do processing in the fixed or not the fixed, but in different ways of dealing with data processing. So there are fixed windows, which basically defines like every 5 seconds we get a result, right? So we have a stream of data, and every 5 seconds we're spinning up some result. Sliding window allows you to have similar thing, but there's multiple windows and a different result. You can say, okay, have a 5 window, but I need to get a result every second. 5-second window and the result every second. And session, a session window allows you to define a window per user, for example, like this, right? So we do have some data based on the event time, processing time, things that arrive in our system, and using the window, we can sort of organize and process this event in this particular form. Now, it depends on the use case. So it's really about what kind of application you're building and what kind of result you want to get from the system. So I really love this game, but I cannot play this on the plane because it requires constant internet connection. However, there's some limited functionality in this game, and I can still play it in a plane, but when the result will be updated only after when I arrive and will connect this into the internet. Now, in this particular case, this is a good example of so-called like late data, right? So there is very common when some events might arrive later. So specifically, this gaming application, it's getting some of the events, and after that, it collects the statistics, my scoreboard, my leaderboard, and things like that. So how are we going to deal this, right? Typical use case, you're playing, or you can send emails, things like that. And after that, when internet connectivity restored, so my phone will send emails or send the game data. So in this particular case, system, when they have this event time semantic, your system still will be able to process it. Either it's going to be window processed, or depends on what kind of window you define. But here's the trade-off as well, right? So if you do like very big window, in this case the memory consumption would be bigger, so potential system might crash because it needs to store state in the processing like vertex, right? Or you can reprocess. And this is also beauty of systems like Kafka, that because it stores all the events, you can actually replay all these events, including the events that arrive later, and adjust result based on that. Results. Yes, it's possible to get computation results in the real time, so don't need to wait over overnight computation. So the windows allow you to build or group events and build some of the results based on this. So basically, window is a way how you can group arriving events, and systems like, for example, Kafka Streams can also provide the semantics for processing late events. So how many of you see sleeping people in the audience? Okay, so we saw a couple of those. Anyways, so sorry for initial delay, and sorry that I had to a little bit rush it up. So this particular link leads to Kafka Stream examples. There's not only Hello World. There's many examples, including like a real-time application that calculates rating of the song based of the place. There's runs some simulation, and you can query this application, and over you see the rating based on the players. There are a bunch of examples that shows how to deploy this. Even you can deploy it with Docker container. You can deploy it using or run it locally using Docker Compose. This actually is a pretty extensive collection of examples. Windowing examples there, examples how you can. There's another feature that I haven't spoke today. It's called interactive queries that allows you also query data in a fashion of similar ways how you can do it from other systems or databases. And also recently, a couple of weeks ago, we announced this project called KSQL, which basically allows to write streaming application using SQL. So it's also pretty cool. Like you can without even like writing Java code in interactive console, you can write like word count applications or like fraud detection applications. Thank you very much for your time. If you have some questions, feel free to send those to me. It's my email, it's my Twitter. If you have a Twitter, you know what to do, right? I will upload this somewhere, and I will post the video also somewhere for those of you who didn't come, but next time hopefully we will. And thank you very much for your time.